Well, let's talk about global warming, something I'm sure you've heard about. You probably know something about, but we definitely need to make sure that you have a pretty solid understanding of it. It's one of the most important. No, it is the most important thing that we are facing as a society today. It's the most important thing in environmental science, and it's going to affect you in your lifetime. So let's learn about it. So let's start off with this. There is a big difference between climate and weather, and there are people, a lot of them in the United States, who are what we call climate deniers. They mistakenly go like, "Well, it was cold today, so therefore there's no such thing as global warming." And it's very important that we are able to win this argument because the only way we're going to turn around the tide of carbon dioxide that's changing the temperature of our world is if we can get people to understand how important it is for us to do so. We have the ability to change this problem. We do. We simply have to accept that it is a major problem and get people to act accordingly. So the problem is right now, most people in the world, they may be aware of it, but they don't really take to heart how dire the situation is, and they need to. And that starts with understanding the difference between weather and climate. So weather is just the day-to-day changes that we find in things like how hot it is, how cold it is, whether it's raining, whether there's high pressure, low pressure, whether it's windy, whether it's raining or snowing or sunny. That's weather. And the thing about weather, if you've ever tried to like plan for a trip or whatever, it's inherently unpredictable. It's very difficult to know what the weather is going to be a few days from now, much less a week from now, much less a month from now. It's impossible. Even with all of our modeling and AI, we can't predict weather. Climate is another story. Climate is the averages over many years. So if we look, if you were to go to say, I don't know, Antarctica, I bet you would pack stuff for cold weather because you know it's going to be cold there. You know why? Because year after year after year, it's cold there. If you were to go to Korea in the summertime, you'd go, you know what? Going to Korea in July, I probably don't need a jacket. I know it's going to be hot. It's probably going to be raining. So climate is the patterns that we see that are pervasive, that are clearly demonstrable and reliable. So if we just measure temperature, humidity, rainfall, hours of sunlight, whatever, all the time, year after year after year, which we do, and you compile that and average it out, that's what climate is. And climate does not change very rapidly. It's very predictable. But when you see it changing, you know there must be an underlying mechanism for making it do so. And climate is changing. That's why we sometimes call it climate change. Now, one of the reasons we call it climate change rather than global warming is because there are places that are actually going to get colder as the world gets warmer, at least initially. So the planet overall might be getting warmer, but certain locations, because maybe the movement of an ocean current, are going to get colder. So therefore, scientists have decided that maybe a better term for it is climate change. But make no mistake about it, overall, the planet is getting warmer. So I'm going to try to convince you of in the course of this screencast. I guess I just talked about that, so I don't need to talk about that right now. I got ahead of myself. I sometimes do that. Okay, let's talk about the mechanism here, okay? All right, now just work with me here. The idea is this. Light from the sun, it comes in the visible part of the spectrum, mostly, all right? That's the light we can see with our eyes. And some of this is going to reflect off clouds and bounce into space. It's never going to get to Earth. But and some of it will hit the Earth and bounce off and go back into space. The ones that reflect off Earth or reflect off the clouds, they have nothing to do with Earth's temperature. They have nothing to do with what we call our energy budget. However, a significant amount of the light, and I like the way this graphic shows by the thickness of the arrow how much, a significant amount of the light energy that hits the Earth's surface is absorbed by the Earth's surface. And remember, you can't create or store energy. So if I absorb light from the sun, light energy from the sun, how is it going to manifest itself? As thermal motion of atoms. The atoms are going to jiggle faster, the world gets warmer. Well, here's the thing. When atoms jiggle, they make light. Now, the sun is at like 5,000 degrees Celsius, 6,000 degrees Celsius. So you know what? The atoms there jiggle fast enough to make visible light. The atoms of the Earth are more like 15 Celsius. And you're like what, like 30? Well, I take your temperature all the time. You're like 36.5. Okay, except some of you were always a little bit over 37, but not quite 37.5. It makes me crazy. But the point is, we're giving off infrared light. That's what those little thermometers are detecting. The Earth gives it off too. Now, here's the deal. Some gases, like carbon dioxide and water and methane, they are able to interact with the infrared light and keep it from leaving Earth. So a lot of it tries to leave the Earth, but only a small amount of it gets into space. Consequently, that recaptures a lot of the energy that came in from the sun, and that keeps our atmosphere warm. So this is a really important aspect of our atmosphere. And I remember carbon dioxide makes up this tiny little fraction of the atmosphere. It's like 0.04% of the atmosphere. It's not much, but it's an important thing because without it, the world would be quite cold. Now, so again, here we go. Visible light comes in from the sun. It hits the earth. The earth gets warmer. The earth gives off infrared light. Now, when that infrared light interacts with greenhouse gases, we're talking about water, methane, and CO2 is the main one. Then those molecules of, say, CO2 captures that when that. So here it is. This light comes in from the sun. We're going to try to keep here. Hits Earth, bounces back up. I'm sorry, it gets absorbed, gets radiated out as infrared light. And when it hits CO2, the CO2 starts to jiggle. When the CO2 starts to jiggle, what does it give off? Infrared light. Which way does that light go? In all directions. And guess what? Almost half of those directions are going to carry it right back into the Earth. So CO2, by absorbing infrared light and then re-radiating infrared light, it sends a lot of it back to Earth and it slows down the rate at which it escapes into space. Now, water vapor is a great example to help you understand this. This is a phenomenon that most people I know have observed. If you have a night where it's cloudy, it tends to not be very cold. The cold nights, when you really suffer when you go outside, they're almost invariably clear nights, and here's why. At night, well, during the day and at night, infrared light is leaving the Earth. When it's cloudy, the water vapor is a greenhouse gas. It absorbs that infrared light and it re-radiates it, and half of those directions in which it's re-radiated come back to the world. So we give off energy, but then we get it back. We give a half of it back, so it doesn't get as cold. Whereas on a clear night, that water vapor isn't there to absorb it. So those infrared photons just keep leaving the world, making it colder and colder and colder. So just as water vapor can make the world warmer, so can carbon dioxide and methane and a few other gases. But the main one we should concern ourselves with is carbon dioxide. Without carbon dioxide, look what happened. Without carbon dioxide, the world would just freeze because there'd be nothing to keep the infrared light in. So we'd absorb energy from the sun, but then we'd lose it, and the temperature of the Earth would definitely be below 0 Celsius. And in fact, this has happened to there is geologic evidence to indicate that there have been at least one occasion in Earth's past where we had what we call snowball Earth, where the world just became this frozen ball for a while until we got enough carbon dioxide to warm it back up. So as I said, here are the basic, gases that we consider greenhouse gases. Those are ones that interact with infrared light. Carbon dioxide is by far the most predominant one in our atmosphere, followed by methane. But methane is only like 1/8 of what carbon dioxide is in terms of its amount. Although methane is a little bit better at being a greenhouse gas. The NO2 that comes out of car exhaust is another one. And then these fluorinated gases, these are things that create a problem with the stratospheric ozone, but they're a very small amount in terms of greenhouse gas emissions. So if you look, we're just going to focus on carbon dioxide. It's where the problem really is. Now, why is it a problem? Well, what happened was this. Prior to the 1800s, we can go back to the 1690s, okay? The only way we released energy apart from eating was by burning wood. When you burn wood, you're basically releasing energy that tree captured over the course of its lifetime through photosynthesis. So, we're talking about carbon dioxide came out of the atmosphere into a tree, and then you burn the tree and it went back into the air. So you're basically cycling it, from the atmosphere into the tree and from the tree back into the air. And really, that's sustainable. It doesn't really significantly change the percentage of carbon dioxide in the atmosphere. And one thing to keep in mind is, if you chop the tree down and you put more carbon dioxide in the atmosphere, more carbon dioxide lets trees grow a little bit faster. So it was sustainable, right? It didn't change the level of carbon dioxide for the entirety of human history prior to the 1700s was about 275 parts per million. But then we realized, you know what? This stuff in the ground called coal, if you burn it, you can boil water, and when you boil that water, you can make that water develop steam pressure, and that steam pressure can then be used to push a piston, or to turn a generator. So basically, what happened was once we learned to do that, people started burning coal to do work, and that suddenly changed the energy budget. Now we're digging carbon out of the ground where it's been for hundreds of millions of years and putting it in the atmosphere. At first, it wasn't that big of a deal. It wasn't that much, but then in the later part of the 1800s, people developed what's called the internal combustion engine. And that is one that allows us to burn liquid fuels like gasoline and diesel. It basically makes small explosions inside these metal pistons, and that was ideal. It was easily transportable, so you could have small scale like cars and trucks and tractors. So for small scale, uh, a few people being transported around, it really changed the transportation industry. Well, again, now we're taking oil, which is carbon comets have been in the ground for millions of years, and we're releasing them into the atmosphere as carbon dioxide. So between those two things, that really made a big change. So here's the deal. If I take coal or gasoline or natural gas, I notice that in all cases, coal is essentially carbon with some impurities. You combine it with oxygen, it burns, you get heat, and you get CO2. Gasoline, like C8H18 octane, you combine that with oxygen, you get CO2 plus H2O if you get a perfect mix. All right. In both cases, look what you're getting: carbon dioxide. There's all fossil fuels are going to produce this. And so we dump these in the atmosphere faster than it can come out of the atmosphere. There's our problem. So what we find is each year we dump billions of because and the other thing is we learn to make electricity. And the way you make electricity is you spin a coil of wire between magnets. And how do you make it spin? Well, you boil water, you make steam. So you burn coal to make steam, just like you do in a steam engine, train, and you use that steam pressure to spin a propeller, and that propeller, called a turbine, spins the magnet inside the coil of wires, or vice versa. The next thing you know, you're generating electricity. Well, we become very reliant on that to the point where, look, between 1998 and 2018, just in that short time span, we went from having but putting 25 billion tons of carbon dioxide in the air every year to like 37 billion tons, 36 billion tons of carbon dioxide in the air every year. And this isn't slowing down. I mean, we're just doing it faster and faster. We're just dumping carbon dioxide in the atmosphere. And that is what's causing a change in the temperature of the Earth, because every one of those molecules is able to block infrared light from leaving the planet. So the more carbon dioxide you have, the less infrared light leaves the planet and the warmer the planet gets. It's a pretty simple idea. I just wish people would take it to heart. Look at this graph here. This is pretty startling. What we see here is this: that in the year 1000, all the way up for 1,000 years, basically, the carbon dioxide levels was well below 300. The industrial revolution happened. We learned how to burn fossil fuels and make engines to make things move, to make things spin, to make electricity. And then it really started going. And then World War II happened. And after World War II, then the entire world began to industrialize. Every country on the planet started to hook itself up to the electrical grid. Every country on the planet started to provide motor vehicles to the people who live there. And the demand for carbon fuels skyrocketed. And now we're just screaming upwards like COVID in America. It's crazy. So so this is where we are right now, and this is not where we want to be. We'd like to get back down to here, and there are ways of doing it. But for today, we're just going to talk about the consequences of this. Now, this is a graph that's a pretty interesting one. I definitely want you to be familiar with. So this is basically, there's a monitoring station for atmospheric gases on the top of Mauna Loa volcano in the middle of the Pacific Ocean in Hawaii. They put it there because it's pretty far from any other industrial sources. Hawaii's not particularly industrial, so it's fairly clean air. And it's high up, it's like, I don't know, I want to say like 6,000 meters up, something like that. So you have this pristine air, and they just monitor the atmosphere and see how is the atmosphere changing. And here's what they find. Okay, so when the year I was born, around 1962 is when I was born, the percentage of CO2 in the atmosphere was down here below 320, so like 317. Now it's here, like I'm seeing 58. In those 58 years, it has gone from 317 to 417. That's a really significant increase there. And this shows no sign of slowing down. And one thing I want to point out that is kind of cool here, though, is this. Notice how it goes up and down and up and down, up and down. Well, here's a hint. Hawaii's in the northern hemisphere. In the northern hemisphere, in the summer, there's more productivity. So we find is when there's more productivity is photosynthesis, that takes carbon dioxide out of the atmosphere, combines it with water to make sugar. So we find is when we're below the trend line here and here and here, these lower points, those are during the summer when carbon dioxide is being taken out of the atmosphere by photosynthesis. The higher bumps here, here, and here, and here, that's during the winter when photosynthesis is occurring a lot less, but respiration is happening just as much, so it goes up. Now, overall, this trend has nothing to do with photosynthesis or respiration. It has to do with the fact that we have what we call anthropogenic, human-made carbon dioxide being dumped into the atmosphere. And I want you to go back, look at this. Look at this trend line here, right? Carbon dioxide levels just skyrocketing upwards. And now look at this. This is the temperature of the Earth. Now, it's very difficult to measure the temperature of the Earth. There's so many different ways you can do it. But there's mechanisms. There's ways of averaging out. Here's what we find. The temperature of the Earth was fairly low, and then all of a sudden it started climbing up. And as a consequence of all this carbon dioxide we're putting in here. And the world is really definitely getting much hotter. And it was sort of hypothetical when I was in college. It's like undeniable right now. That who believes it more than anyone else? The insurance companies, because they're going to pay so much money in terms of like fire damage and flood damage. It's real. And take a look at this. This is from 1880 to 2010, and this is basically, we'll say this is what the average temperature was prior to industrial revolution. All right. And basically, there's some years where we're colder than that, and then we had some warm, and then some cold, and some warm, and some cold, some warm, and some cold, and then what happened? Starting here, like in the mid 1970s, there hasn't been a single year that's been below average. In fact, it just goes up and up and up and up. So the temperature definitely, this is the tipping point. At this point here, the world started getting hotter as a consequence of all the carbon dioxide we put into it. In fact, look at this. The 10 hottest years ever recorded on the planet have been recorded since 1998. And look at this, okay? 2016, 2019, 2015, 2017, 2018. Look at that. The 5 hottest years were the last 5 years. This is a real thing, all right? And as we know, the source is carbon dioxide. What do we have to do? We have to get the carbon dioxide out of the air. We've got to quit putting it in there and find a way of taking it out. We do that, we've got it solved. And there are ways of doing that. But the trick is to get people to believe they need to do it. And here's one way to get you to believe it. Take a look at this graphic. I'm sorry, it's kind of a bummer to look at. It's scary, but take a look at this. Look at the date down here. I want you to look at these dates. Red means hotter, by the way. Blue means cooler. So what I want you to see is that the temperature of the world changes in different places, but overall, if you average it, here's what you find. Not good. And so what we're going to be talking about with the remainder of the unit is like, how is it though? How are we going to go about fixing this problem? It's no good to just talk about it. We need to figure out a way of fixing it, and that's where we're going to go with this unit. Sorry to talk so long. See you guys later.